Hey yo, what's up? We're going to be looking at some energy conservation today. This is going to be going along with the practice in your packet, but I'll go ahead and talk through it. If you don't need the talk through, then just skip to the end of each question. You can check whether you got the question right or wrong, but if you need a little bit of help, this will kind of help walk you through it. All right, so here we go. All right, y'all, have a read through the question. You can pause it if you need to, but I'm going to go right into it. Now, remember, the point of this is we're trying to do two things. We're trying to show that we can answer the question using kinematics, and we're also showing that we can use the information to use conservation of energy. All right, so I'm going to go ahead and do kinematics first because that's what we're a little more comfortable with. So dropping the ball from my roof, and we know that the speed of the ball right before hitting the ground is 14.2. So if I'm using kinematics, I'm going to go with x naught, x, v naught, v, a, and t. I know the initial position is going to be however high my villa is, the roof of my villa. So that's x. That's the question that it's asking. Determine the height that it's dropped from. So my initial position is going to be there when I'm dropping it. Now I know that at that position, if I drop it, the initial velocity is 0 meters per second. Now, I'm going to say my final position is 0. That's down at the ground. Now, when it's at the ground, I know the speed because I used the video analysis and I was able to get 14.2 meters per second. And with that, I know, of course, that when an object falls with no other forces other than gravity, because air resistance is negligible, I can go ahead and make the acceleration 9.8 meters per second squared. So you'll notice I don't have time, but the question's not asking about time, so I'm going to ignore it completely, not to leave him alone. Time's a nice little guy, but we're going to ignore him this time. And I'm going to choose the kinematics equation that will allow me to answer that question without time. So I'm going to go with that v squared equals v naught squared plus 2a x minus x naught. I'm going to go ahead and throw those numbers in. I've got the 14.2 squared. I've got the initial velocity, which was 0 squared, and then I've got the 2 times the a, which is negative 9.8. Please remember to make it negative because it is down. My final position is 0. The x naught is that x. That's what I'm looking for, remember. And so now I should be able to just kind of solve. I can do 14.2 squared, which is 201.64. And then the 0, of course, is just going to be 0. 2 times negative 9.8 is negative 19.6. And the 0 minus x is going to be a negative x. I can just get rid of the negatives there. Negative times negative is positive. And now to solve for x, I'm going to divide both sides by 19.6. And I get an answer of 10 point. Yeah, I'm just rounding it. And the 10.3 then will be meters because I am solving for position there. So, ta-da, we got that the height is 10.3 meters. All right, now we want to show that we can get this same answer by doing conservation of energy. So we're thinking about at the top of the building, the object is at rest, right? We were talking about that before. At the very top, it's at rest because I'm dropping it, which means it doesn't have any kinetic energy. It has gravitational potential energy because it's some height off the ground. So initial, we'd say, well, there's no kinetic energy. There's definitely gravitational potential energy. And, of course, there's no elastic potential energy because there's no springs or stretching things. So that's all we have at the beginning. And that should be equal to whatever we have at the end. Now, what we have at the end is right before the ball hits the ground. Right before the ball hits the ground, its height is going to be 0, so there won't be any gravitational potential energy left. It'll be going pretty fast, so it's definitely going to have some kinetic energy. So this is at the final being right before it hits the ground, so we got the kinetic energy. And, of course, we still don't have elastic potential energy. All right, so each time I think about the energy, I'm thinking about those types of energy, the gravitational potential, the kinetic, and the elastic potential. And I figure out which ones of those it has and which ones it doesn't have. Now, of course, at this point, I should also think about, is any work done? And the answer is no, because the only force is gravity, and gravity is accounted for in our gravitational potential energy. It's what we call a conservative force because we consider it in our conservation. So therefore, we can go ahead and put mgh initial in for our gravitational potential energy, and we'll put 1/2 mv squared final in for the kinetic energy. And you'll notice that I didn't give the mass of the ball in the question. It really doesn't matter because see how mass is on both sides here? I've got mass here and mass here. And so if I divide by mass, if I divide this side by mass and divide this side by mass, those masses are actually going to cancel out. And so it really doesn't even matter that I don't have the mass. So on the left side, I am going to have gravity, which is going to be 9.8. Remember that energy is not a vector, so it doesn't need the negative. And then I have the height, which is what I'm hopefully trying to solve for. And then over on this side, I'm going to have the 1/2, the mass canceled out, and I've got that final velocity, which is 14.2 squared. And so now I can multiply those. So I'm going to do the 14.2 squared, which remember was this 201.64. And if I have the 201.64, I multiply that by 0.5. I'm going to get 9.8 H naught equals 100.82. And then I just divide both sides by 9.8. And I get that H naught equals, how about that? I get 10.3 again. All right, so we got the same thing, both using kinematics and energy, right? Now this is great. Not every situation will allow you to do it both ways, but what we're trying to do is recognize that energy works. We know kinematics works, and we're seeing little by little that if we're careful with the energy works too. All right, let's go on to the next question. Let's see what next. Again, you can go ahead and read the question. I'm not going to read it out for you, but we are trying to determine the speed at which the rocket must be launched to be able to get up to that 60 meters. All right, again, we're going to go ahead and use kinematics first. So we're going to go x naught, x, v naught, v, a, and t. We're going to start at the ground, and it's going to go up to 60 meters. We have the initial velocity. That's actually what it's asked for, determine the speed at which it must be launched. So we're trying to find that initial velocity. Now, remember that its maximum height here is 60 meters. Now, if its maximum height is at 60 meters, then we know that the velocity at that point, at the very top, is 0 meters per second. It always is 0 at the very top if there's no sideways motion. Now, if it's a parabola, if the object's moving like this, it's a different story because up at the top, it'll have some sideways motion. But in these situations where we're just shooting it straight up, and it's coming straight down, up at the top, our velocity, that velocity at that point is always going to be 0 meters per second. Of course, the acceleration is negative 9.8 meters per second squared because, again, once it leaves the launcher, it will have only gravity acting on it. Now, you'll notice again that we don't have time. Sorry, time. We're leaving you out again. Hopefully, we'll involve him pretty shortly, but time's just missing out today. So again, we're going to use that same equation. V squared equals V naught squared plus 2a x minus x naught. If we go ahead and put the 0 in for the V squared, the V naught, that's actually what I'm looking for. And then plus 2 times negative 9.8 times x minus x naught. The final x was 60 minus 0. All right, and so then this is very similar to the one that we did in class. We're going to do that 2 times the negative 9.8 times the 60, and we should get 1,176. So I've got 0 squared equals V naught squared. So I guess the 0 squared is just 0. That's fine. And then I've got a minus 1176 here because it was a negative times a couple of positives. I'm going to add the 1176 over to the other side, and then I'm going to square root it. And when I square root the 1176, so I'm going to add, so I'm going to do that first. I'm going to go ahead and show that. I'm going to add the 1176 to the other side. And then once I have the 1176 on that side, I'm going to have the V naught squared. I'm going to square root both sides. And the square root is 34.3 meters per second is the initial velocity that is required in order to get it all the way up to 60 meters if I shoot it straight up in the air. All right, now we actually did that in class, but this is a good reminder. Let's go ahead and look at how would I get that using energy, all right? So we need to think about the initial position and the final. Now this is, again, very, very similar to the kinematics, right? We need an initial point and a final point. So the initial point is going to be the speed right when it's launching, okay? Not the beginning, because the beginning, there's an outside force. There's going to be the force of the launcher pushing it upwards. And I don't know how much force is there. It actually asks that in the next question, right? Letter B says, what is the average force? So I'll get there eventually, but right now I don't know that. So I'm going to assume that we're starting with the speed right as it leaves. Now, it's up to you. At this point, I'm going to just go ahead and say, okay, so if it's leaving at that point, it's pretty close to the ground. It's almost on the ground. So I'm thinking about my gravitational potential energy, my kinetic energy, and my elastic potential. Okay, now if we want to be technical, recognize that there would be some gravitational potential energy. You know, if we're looking at the picture here, it starts on the ground and then it actually goes up in the air, and it's about 30 centimeters up in the air. See, I can see that 30 centimeters in part B here. And so it is actually 30 centimeters up in the air. But like we talked about in class, that 30 centimeters is going to be so small compared to the 60 meters that it is in the air that it's probably going to be negligible. If that's still hard for you to kind of think about, come chat with me in class and I'll talk you through it. We can do the math and see what it would look like if we did that 30 centimeters and if it would actually change anything. All right? Being what it is, we're going to go ahead and say at the beginning, it does not have gravitational potential energy. It is shooting off of the launch pad, so it definitely has some initial kinetic energy and definitely not elastic potential. Now, at the end, when it gets all the way up to the top, we know that it does not have kinetic energy because its velocity is 0 up at the top. Again, no elastic potential, but it's definitely going to have its maximum gravitational potential. So what's happening as the rocket goes up is that the kinetic energy is turning into gravitational potential energy. Kind of the opposite of the one that we did previous, the one that we just did. So in this one, we're going to go 1/2 mv squared initial must equal the mgh final. Now, hopefully you recognize this is similar to the last one. I don't have any mass, but hey, that's okay. I don't need the mass because I can divide both sides by whatever the mass is. And the mass is going to cancel out. And so we're left with, on the left side, 1/2 times that v naught squared. That's what we're solving for. And then on the right side, I've got the g, which is 9.8, not negative 9.8. Please remember that that 9.8 is the acceleration of gravity, but it's not a vector, so we don't need the negative. And then we'll go ahead and put in the height, which is 60 meters at the very end. So now we can actually go ahead and do that math. We'll do 9.8 times 60, which is 588. Which is going to be equal to the 1/2 v naught squared. I got to get rid of the 1/2. So you can either divide by 1/2. I like multiplying better. My brain works better with multiplication. And I get that v naught squared is equal to, oh, that looks familiar, 1,176. Look at that. And we're going to square root it. And guess what? We're going to get the same thing as last time. Woo! And we got 34.3 meters per second. So we got the same speed using conservation of energy, knowing that all of that kinetic energy is going to turn into gravitational potential energy as it gets to the top, and that will give us that initial speed. Now, part B says the launcher has a length of about 30 centimeters and asks what is the average force that the air must exert on the rocket. So remember what's happening is that it's starting on the launcher, and then the launcher is causing it to gain energy because it started at rest. At the very, very beginning, it was at rest. It didn't have kinetic energy. It didn't have gravitation, but it didn't have any kind of energy. And so we're getting that external force, that outside force of the launcher pushing up on the rocket. And so that force, we talked about work is equal to force times distance. Now, work is the amount of energy that's added. It's the change in energy. So at the beginning, it had 0 kinetic energy. And once it's lost, it has kinetic energy as it's being launched. So I can actually calculate how much energy it had, how much energy the launcher gave it, just by doing 1/2 mv squared. Now, alternatively, you could say, well, I know that that's the same as the final gravitational potential energy, so I could just do that mgh. Totally up to you. But I'm going to go ahead and say that the total kinetic energy that I have there at the beginning is equal to the amount of work, the amount of energy added in by the launcher. Then that's going to be equal to the average force times the distance. The launcher has a length of 30 centimeters, which is 0.30 meters. And so I'm going to put that in for the distance for which that force is being exerted. I don't actually know the mass, so I'm going to have to find that. So yeah, I just went and looked it up. The mass is about 200 grams. Now 200 grams, I got to be careful with that. 200 grams is going to be 0.200 kilograms. And then I know the speed, the launch speed was that 34.3, which needs to be squared. That's going to equal F times that 0.30 distance. So I'm going to do 1/2 times 0.2, that 0.200, and then I'm going to multiply that by the 34.3 squared. All right, and I get 117.649, which that then needs to equal the force times that distance over which the force is exerted. So I can divide by the 0.3 on both sides, right? Divide by 0.3 here, divide by 0.3 here, and what I get is 392. I'm going to go 3 units. It is a force, and forces have units of newtons. So the average force will be about 392 newtons. So there you go. That is question number 2. Let's move on to question number 3. Question number 3 here is, you can go ahead and read it. We got a spring-loaded dart gun launching with a speed of 4.3 meters a second. If I were to shoot it straight up in the air, how high would it travel? All right. So let's go ahead and we go kinematics first. I think we're getting really good at this. So we're going to say that we start at a height of 0. The question is, how high is it going to go? So I'm going to put an X there. I know it's going to start at 4.3 meters per second. That's the launch speed. I know when it gets up to its maximum height that its velocity is going to be 0 meters per second. Hopefully this is getting more comfortable. And the acceleration, of course, is 9.8 meters per second squared. Negative because the acceleration is downward. So again, poor time gets left out again. We're going to go v squared equals v naught squared plus 2 times a times x minus x naught. And we throw those numbers in. So we're going to have 0, I can speak, 0 squared equals v naught, which is 4.3 squared, plus 2 times negative 9.8 times x minus 0. And you'll notice that that then is going to simplify to 4.3. The left side is going to be 0 squared, which is 0. I'm going to have 4.3 squared. So it's going to be 0 equals 18.49. And then 2 times negative 9.8 is negative 19.6. X minus 0 is still x. So like this. You can either subtract the 18.49 to the other side or add the 19.6. I like the x to be positive, so I'm going to go ahead and add the 19.6. You should get the same answer if you subtract the 18.49 over. The only difference is you're going to have negatives there. So I'm going to have 19.6x equals 18.49. And so I take that 18.49 and I divide it by 19.6, and I get x equals 0.943 meters. Ta-da! All right, so not too high, but it wasn't going very fast either. Now, to make sure, let's go ahead and check using conservation of energy. So we know that we're going to start with a speed of 4.3. So remember, we're looking at gravitational potential, kinetic, and elastic potential. So initial, what do I have? Initially, I've got kinetic energy, right? Because it's starting with that speed. If it starts with a height of 0, then it doesn't have gravitational potential. And if it's already moving, then there won't be any elastic potential energy. Now, the elastic potential energy will be important later when we look at the spring being compressed. But right now, if we're saying that our starting point is this point where it already has this speed, then there won't be any elastic potential energy there. All right. Now, if we look at the final energy, again, this is going to be very similar to the other ones, is that it's getting up to its maximum height. The velocity is going to be 0, which means it's not going to have kinetic energy. It will be at its maximum height, so it's going to have some gravitational potential energy final there. And again, it won't have the elastic potential. And so we'll go 1/2 mv squared initial must equal the mgh final. And just like the other two, we're going to divide by m. The m is going to cancel out, and we'll be left with 1/2 times the initial velocity, which was 4.3 squared, which is going to equal 9.8 times hf. That 4.3 squared, remember, was 18.49, and I'm going to multiply that by 1/2, so I'm going to have 9.245, which is going to be equal to 9.8 times the final height. I'm going to divide by 9.8 because I can, and also because that's the right way to solve for the final height. And you'll notice that when you punch those numbers into your calculator, I get that the final height is 9.943 meters. It's the same as before. I hope that's not a surprise anymore. Kinematics, conservation of energy, give us the same thing. All right? Now, part B says if the spring compresses 5 centimeters before launching the dart, what would the spring constant need to be? So this is going to be a little bit different. So this is going to be a different initial and final condition, right? The initial here is going to be when the spring is compressed before it's shot. So it's not moving yet, so it doesn't have kinetic energy. Its height is 0, it's on the ground. What it has when the spring is compressed is elastic potential. Now, the final we're going to look at here can be either of the two because there are no external forces. The spring is accounted for in our elastic potential energy. The only forces that are here is the spring pushing our dart and then gravity. And gravity is fine too because that's part of our gravitational potential energy. So it really doesn't matter. You can either choose the final point to be as the dart is leaving the gun, which means that it has kinetic energy and not gravitational potential, or you can do the point at the very top of its peak, which means that it has gravitational potential energy and no kinetic. We know that those two are the same, so it really doesn't matter which one of those we set equal to the elastic potential energy. I'm going to go ahead and use the kinetic energy just because I like using that. And so my elastic potential energy, remember, is 1/2 kx squared, and that needs to be equal to 1/2 mv squared. All right. Now, again, I'm going to need a mass, so I'm going to go look that up. Beep, 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 beep. And I'm going to get a mass that's about 100 grams, which is actually a pretty heavy dart, but we're going to go with it anyway. And it does say that the spring is going to compress 5 centimeters. Now, be careful. You can't put centimeters in here. It does need to be meters. So that's going to be 0.05 meters. So now I think I'm ready to start throwing some numbers in. I'm going to go 1/2 times k times 0.05 squared is equal to 1/2 times the mass, which is 100 grams, so that'll be 0.100 kilograms. It's got to be in kilograms, times the velocity, which was that 4.3 squared. All right, now I can multiply everything over on the right. So if I do 1/2 times 0.100 times 4.3 squared, then I get 0.9245. And then over on the left-hand side, I'm going to do the 0.5, the 1/2, times 0.05 squared. And that's actually going to give me 0.00125K. And then I can divide both sides by that 0.00125. And I get 739.6. Now, we haven't talked about the spring constant very much, but the spring constant has some interesting units. It's newtons per meter. All right, and that's the unit for spring constant. If you want, you can come ask me about that. I'll explain why, but it has to, remember in class, most of the classes we talked about the units and how the units of 1/2 mv squared are the same as the units of mgh, and the units of that therefore need to be the same as the units of 1/2 kx squared. In order for that to happen, the units of the k here need to be newtons per meter. If you do that, then you'll get the same units as all the other types of energy. All right, so there we go. We were able to find the distance that it went up in the air. We were able to find the spring constant, and we've done some different things, both with kinematics and also with energy. So I hope that was helpful. I hope you're able to check your answers, and I'll see you next time.